Hi, I'm Yang Wei from University of Twente. Today I'm going to present our work, Flow-Based Game for 3D point cloud generation from a single image. It's a joint work with George Wasserman and Michael Yang. In this work, we focus on the task of single-view 3D shape reconstruction with 3D point cloud representation. Given a single object image, we try to generate the whole 3D shape of the object. This is actually a challenging task because 2D image contains limited information for modeling the 3D shape. Motivated by the recent success of deep generative models in the 2D domain, more and more effort has been made on single-view 3D shape reconstruction task. As you can see, given a single image, early methods can generate 3D point cloud, mesh, or voxel. Typically, they employ encoder-decoder structure and introduce reconstruction loss. However, they can only produce 3D shapes with limited resolution. Taking point cloud generation as an example, they formulate 3D point cloud as a matrix with fixed dimensionality, so they predefine and fix the number of points. Recently, some methods based on normalizing flow bring new ideas for point cloud generation. They regard the point cloud as samples from a distribution of 3D points. This formulation allows sampling with arbitrary resolution. Through the learned invertible transformation, the distribution of 3D points can be approximated from a simple prior distribution, such as Gaussian distribution. It's observed that these flow-based methods generate more evenly distributed point clouds. However, they have difficulty in generating clean and detailed 3D shapes. Based on the related work I just mentioned, there are two research questions. Early methods usually consider the point cloud as an n by 3 matrix, and they generate a fixed number of points, which limits their flexibility. On the other hand, recent flow-based methods produce point clouds by sampling from the distribution of 3D points, which can generate arbitrary resolutions, but the generated 3D shapes probably have noises and low-quality details. So, to solve these issues, we propose a new method for 3D point cloud generation from a single image. Well, this slide shows the overview of our method, which is built on a generative adversary framework. It consists of a flow-based generator and a cross-model discriminator as shown in the figure. If you look at the solid lines, the generator is trained to reconstruct the ground truth point cloud conditioned on the image. Besides, the discriminator is trained to distinguish the ground truth from the generator's prediction. By using an adversarial training strategy, the generator is expected to produce high-quality point clouds under the guidance of discriminator. After the training process, we employ the well-trained generator for inference. Let's say, given an input image, an encoder maps it to the latent space, and then a flow model transforms the Gaussian prior to a distribution of 3D points, which allows us to sample point clouds with arbitrary resolutions. Now, let's get into the generator's training details. Taking the ground truth X as input, an encoder phi outputs a latent vector Z. Based on it, the flow model theta learns the invertible transformation between Gaussian prior distribution and the distribution of 3D points. In addition, the image encoder psi maps image I to the latent Z. Because the generator aims to approximate the distribution of 3D points, we formulate it as a conditional distribution Px given I. Correspondingly, the model is optimized by minimizing the negative evidence lower bound. Here, the first term is to reconstruct 3D points, and the second term is to reduce the KL divergence between two posterior distributions of Z. We can see that the flow model which acts as a decoder plays a role in the generator. Here we adopt a fine coupling layer as a basic module to perform such invertible transformation. Different from previous works which rely on multiple flow models for decoding or additional shape flow for modeling the shape latent, our generator simplifies the pipeline and only employs a single flow model for decoding, which reduces the computational costs and inference runtime. Now let's move to the discriminator. Basically, it starts with encoding 2D and 3D features by the domain-specific encoders, EI and EX. After concatenation, the cross-model features are fed into MLP layers to output a value. It's expected as 1, which means the real samples if the 3D features comes from the ground truth X. On the other hand, it's expected as 0, that is fake samples if the prediction X hat is input. Here, we optimize the discriminator D by minimizing the least square loss. Specifically, the first term aims at the discriminator trying to distinguish between real and fake samples, while the second term aims at the generator's prediction trying to be as real as possible. In this way, the generator can be guided to produce high-quality point clouds which are reasonably conditioned on the input image and also exhibit a 3D structure similar to the ground truth. The experiments are mainly conducted on the large-scale synthetic dataset ShapeNet. Also, we evaluate our method on the real images from Pascal 3D Plus dataset. First, we compare our method with recent flow-based methods on 3 major categories of ShapeNet, including airplane, car, and chair. In this case, all the models are trained and tested on a given single category, and for each 3D point cloud, we sample 2,500 points to ensure comparability with prior work. It can be observed that our method achieves the best performance in terms of the evaluation metrics CD, EMD, at F1 score. Here are some examples on airplane generation. Compared to prior work, 3D point clouds generated by our method demonstrate cleaner global shapes. And here are the car generation examples. Although the single-view input image is sometimes not informative, our method is able to generate more realistic point clouds close to the ground truth. Also, we can generate higher quality point clouds with more local structures, for example, the chair legs and the chair caster wheel shown in the figure. The model trained on ShapeNet is also tested on the real images from Pascal 3D Plus. We can see that our method has the potential to be applied to real images which are more complex than the synthetic ones. To further verify the generalization ability, we train and evaluate on all 13 categories of the ShapeNet. In this table, we compare with related works on single-view 3D shape reconstruction. Our method achieves the best CD and EMD and very close to the best F1. Regarding the inference speed, our single flow-based generator performs better than recent works. In ablation studies, we compare different architectures. We compare sampling different number of points, and we compare different samplings with the same number of points. These experimental results demonstrate the effectiveness and the stability of our method. Thanks for your attention. If you have any questions, just feel free to contact us. Our code has been available online. Please refer to our paper for more details. Thank you very much.